Hello, everyone. This is Florian speaking. I'm the project manager for the Multicore, and I'd like to introduce you a little bit in our new product and show you a few slides about how the system works. Let me quickly share my screen. So here you can see our Multicore. So what we are talking about today. So first, I would like to explain you a little bit about the difference between the Multicore and the cluster. You heard a lot about the cluster from Mauro. Thank you for that. A lot of detailed information. I can promise you, I don't have this detailed information for you because we are currently under development, but I show you as much as I can. So really looking forward to show you these things. I will explain you the Multicore technical key facts. Then we will have a look on our stack module, which we use in our Multicore. Then we show you our string, and I will explain you a little bit about the process, the simplified P&ID, how we think we can produce hydrogen here in a most efficient way. Last but not least, I have a small timeline for you, where we are, what we currently do, and when we come to market with this product, or when we have our first demo Multicore in the Bioenergie Park in Saarbeck. So these are our products here. So on the left side, you can see our stack module, which will go in on our EL 4.0, then in the cabinet, and then in the cluster. The Multicore works different. So we have not the AEM electrolyser EL 4.0 in our container. We have only the heart from this electrolyser in our container. We have the herd, the stack, and we have multiplied this by 420. This allows us to reach 1 megawatt of electrolyser power with a shared balance of plant. This is the most important difference between the cluster. The cluster doesn't have a shared balance of plant because we have our single AEM electrolyzers inside. So each stack module has its own balance of plants. This allows us for the Multicore that we have a space optimized and cost optimized product with some redundant components for higher reliability and with an optional dryer. Let's go to the technical key facts. What are our key facts? So this is our product on the right side, our current development status, where we are. It looks a little bit different from the prospect, which you know. This is first time where we show these pictures here in public. We have a H2 production range from up to 210 norm cubic meters per hour. This means that we have around about 450 kilogram hydrogen per day. The nominal power consumption is around about 4.8 kilowatt hours per norm cubic meters. We have a pressure from the hydrogen from 29 to 35 bar. The purity, this is a frequently often asked question, is with dryer. So the dryer is optional from 99 to 99%. So without the dryer, we can reach a hydrogen purity from 99.8%. This is currently under evaluation. It's better, maybe better, because we have also a chiller inside. I will explain a little bit later to you what this subproduct for us do. We have a 40-foot container for our Multicore series. For our first Multicore, for our demo version, we use a bigger container, a 16 by 3 by 3 by 3 meters container. This has maintenance reasons and still under development. We are currently under optimization where we can find space, and but the most reason is that we have more space for maintenance. The hot startup time from hot startup to the steady mode is within seconds, very flexible, and from cold startup to hot startup we can reach it in around about 30 minutes. The flexibility of the nominal production range is 3 to 105%, and the required water what we need is that we need demineralized water already for our container with 5 microsiemens per centimeter on 6 to 30 degrees Celsius. The electricity input is 3-phase 400 volts AC 3-phase grid, basically what Mauro in his cluster used. So let's go a little bit more in detail here. Our stack module. This is not our EL, as you see. This is our stack module, which we use for our multi-core, smart, simple, scalable. So this is basically very simple. So we have the stack, we have an injection molded closure, we have an electrolyte in, we have electrolyte out, and we have an H2 connection. Of course, we have several sensors inside to check the pressure of the hydrogen, to check the flow of our electrolyte, and to check the temperature of our electrolyte. All this information will go to a data acquisition board in the back of this module, and this data acquisition board is connected to our control logic. So the data acquisition board is the heart of our stack module, and yeah, basically this is the stack from our EL 2.1 and EL 4.0. So we expected a lifetime from up to 35,000 hours for each single stack module. And the advantage is that we can replace each stack module individually. So this stack module, together connected, becomes a string. This is a string. Looks a little bit complex, but basically very easy. So the AEM string is made up of 2 stacks. Not of 2 stacks, of 10 stacks, sorry. So the stacks are driven by only 1 power supply unit. And basically, this is then 1 electrolyzer for us. They are connected in series electrically with parallel hydraulic and gas connections. These strings are connected then in parallel to a set. So we have multiple strings and connected to a set. A set is 21 strings. We have 2 sets per multicore, and each set has its own tank and its own cooling system and its own electrolyte pump set. So we can separate the strings individually from the rest of the balance of plant, from the rest of the electrolysis process. So you can cut off the electricity and then you can replace the string individually, or you can maintenance or whatever you want on the string. Yeah. So basically it looks like this. So it's a little bit like a bookshelf. It's on the left, not on the right side on the container. Here you can see 220 electrolyzers in our, let's say, bookshelf, in our rack on the left and on the right side. And they are connected hydraulically in parallel, and the gas is also parallel collected. And you can see these are 10 stack modules, and all of these have 1 power supply unit. So 1 power supply unit, is for this 10 stack modules, 1 power supply unit is for this 10 stack modules, blah, blah, blah here. Yeah. So how does then the process work? Basically, here we have a little P&ID, a small P&ID, to get a simple understanding of the process. So the demineralized water will go in on our electrolyte tank. So the electrolyte tank, so first I have to say we have 2 sets. So basically, this is the same what we do here. So we have demineralized water, so on the top and of the bottom. Demineralized water will go in our electrolyte tank. The electrolyte tank is connected to the pumps, and the electrolyte will pump through the heat exchanger, where we reduce the heat from the electrolysis process to the top of to our coolers on the roof of the container. So then the electrolyte will go in our AEM strings, where we start produce hydrogen. The H2 will go out to the gas treatment, and from there you can use the hydrogen whatever you want for. So you can put it on a buffer tank or whatever you want. The used electrolyte will go with the O2 back in the electrolyte tank, where the O2 will be separated from the electrolyte and will go out to the atmosphere on 0 bar. Basically, this is our process, our P&ID in a simple way, and yeah, that's it. Now we have the detailed design here. So here you can see our detailed design of our multi-core. This is our first product. We are very proud of it. So you can see on the, I need a pointer. So now I think you can see my pointer. On the right side of the container, we have the electrical compartment, and on the left side of the container, we have our process compartment. Basically, it is the same concept which Mauro already explained. So the compartments are totally separated by a gas leak-tighted wall, you can see here. So we have all our electrical stuff on the right side on the container. We have our control board here. We have our power supply units here. So in total, 42. And we have the main power cabinets here. We will enter the multi-core with electricity from the bottom and with fresh water or with demineralized water from the left or from the right side to the tank, whatever you want. Then we have the process compartment where we have our tanks here. We have 2 of it, 1 for each set. 1 tank is here and 1 tank is there. The electrolyte will then go to the pump group. Here you can see the pump group. We have in total 3 pumps. 1 is a backup pump. This is required, or it's not required. We would like to have a high reliability, and if a filter or I don't know doesn't work anymore, then we can choose this pump, and you don't have to stop the process. Then you can maintain easily the other pump during you have a backup pump here. So then here you can see the filters. From here we go with the electrolyte in our heat exchanger. You can see here, and we extract the heat to the roof here. And from this point, we will go with the electrolyte in our AEM sets. Here you can see the AEM sets from the container side, and we have each AEM set, 1 on the left side and 1 on the other side here. It's mirrored. Yeah. From this, we will go in our gas treatment. You can see the chiller on the top of the roof, and we have a dryer here. It's an optional dryer. You can buy it. But this is our demo multi-core. This is the reason why we have included it, to check the H2 quality of our products here. Yeah. To get insights how it looks inside the container, I can show you this. This is basically when you open the door from the end of the container, and you will look inside the container, and then you see this. On the left side, our set, on the right side, our set, in the middle, our pump group. I think it looks impressive. A lot of stack modules inside, each is connected to each other, and this is how our concept is working. And yeah, this is the current status of our detailed design. Now I will come to the project timeline, where we are and what our next steps are. So you can see we are finished our detailed design phase. We are now in the process to start assembling our first demo multi-core. For this, we have a build partner already chosen. In parallel, we have some prototype strings, which we are testing in our P&ID park in Saarbeck. And we have also another one on our build partner side. We assume that the first demo multi-core will be available by the end of this year. Then we start commissioning, and this will be in the Bioenergie Park in Saarbeck, where our factory is planned. The production of the first series of the commercial multi-core will then start after that, and we will deliver the first commercial multi-core by summer 23. Then we will, of course, have a few design updates, but we will build only 10 multi-core 0 series in the first year. This is the plan, before we then have a design update with maybe some other stacks or some design updates and improvements. But the plan is to have only first Multicore 0 series in the first year. Yeah, basically that is from my side. Now I'm ready for questions, and yeah. Hi, Stefan.
So, good morning, everyone. Florian, thank you for the nice presentation. Looks impressive how quickly all of that evolves and how you are doing progress in all the steps and smaller steps, bigger steps. A lot of things to do there, I see. Okay, indeed, we got some questions. So let's start with the first one. They are asking for the flexibility of the multicore. So are the numbers of AEM stack modules fixed in the container?
Yes, for the first multi-core demo versions, they are fixed in the container. So we have 420. This is the reason we choose 420 to reach 1 megawatt. This is a huge mark which we want to meet. And the flexibility, it works with the flexibility. We can shut down strings individually, and then we can also reduce the current, and that allows us to handle with 3% to 105%. Load range.
Okay, cool. So currently you have the flexibility between 210 and 420. In a later stage that might change as well. Okay, and then there's another question. You were showing a slide with a data sheet, and that defines the inlet water temp to be between 6 and 30 degrees. So they are asking what happens if that is just exceeded. So if you take 35-degree water, for example, why that is causing a problem, I think.
I don't think that is a problem. This is a requirement which we have for ELs. So we will heat up the water to 55 degrees. But this is basically standard tap water requirement. So we can investigate what happens if it goes to 35, but I don't think this is an issue. So it will reduce the time to hot standby maybe. So if it's preheated, so then you can get earlier to the hot standby mode. So maybe it's good for you.
Okay.
So shouldn't be a problem.
Good, thanks for that. And then there is a question on the hydrogen chiller. So the question is if the cooling of the hydrogen gas is directly done by the chiller.
Yes, the cooling. So we will cool down the hydrogen up to 5 degrees. This will reduce all the moisture which we have, and then it will go in our dryer. So you have a higher purity with the chiller. You have already 99.97%, but this is not evaluated. That is the reason why we put 99.8 on the data sheet. So you have a better or a higher purity with the chiller as without a chiller, of course.
Okay, thanks for that. Next question goes a bit into the design. So why should we have all the systems in a 40-foot container? What would be the problem if we had one smaller container for the production, so for the electrolyzers, and one or more containers for the skids and aux devices?
So it depends on the space where you want to run the system or to operate the system. I believe, or we believe, that to have it all in one container makes it easier. You can easily scale up it, and that is the reason why we choose one container. Yeah, that is basically the reason why we put it all in one container, to have it as a product and not as 2 products or 3 products.
Yeah, understood. Okay, thanks for that. Ready for another one?
Yeah.
Okay, so talking about the heat in the container, so is it planned that the customer can use the heat that you have in your heat exchangers?
Yeah. Yes, this is planned, and we actually do it for our first customers. So we exchange the heat from the coolers with an additional heat exchanger, and then you can use the heat. You can bring it to a heat pump. You can heat your plant or whatever you want. This is possible. But it is expected that you need more design works for it. But this is what we do for our first commercial series, by the way.
Okay, even a step further, cool. Next question. So what are the pros and cons between the electrolyzer 4.0 and the stacked modules?
There are no pros and cons because basically they use the same herd because they use the same stacks. You can have the pros. This is a smaller product here. So we have no dimensions on it, but it's 300 millimeters long and 300 millimeters wide, or 400 millimeters long and 250 millimeters wide, roundabout. And we have no balance of plant in this product here. So this is only the electrolyzer, and you have to connect it to an electrolyte pump, to electrolyte heater, to a cooling system. Without of these things, this will not work. And this is the reason why we connect it to a string and feed it with a shared balance of plant. So the pros is we can use more of these stacks and we can scale up each stack to 25 kilowatt because we put 10 of these in series electrically. This is the advantage of using these products. And of course, we save spaces for this. And imagine if you have only one power supply unit and not 10, saves a lot of money. So it's cost optimized for the multi-megawatt launch.
Yeah, very important topic to look at that. Agree. Okay, another one that is on in case of a failure in the multicore itself. So can you exchange the stack in case they are not working properly? Can you exchange? Well, it's a bit more detailed question, so give me a second, please. So can you exchange one, too many, or do you have to exchange them all at a time?
So basically, if a stack is broken, then the string will shut off automatically because we will check the status of our products, of our stack modules with the sensors inside. So if a stack is broken, we will separate the string from the rest of the balance of plant and from the rest of the electrolyzer. Then you can maintain it easily. You can replace a single stack module very easily. And then you can start the system again. So this is the idea behind, to have easy maintenance and replacement of stack modules individually.
Yeah, and keep the rest operating.
Yeah.
Right? So I think that answered it well. And then we are getting to the famous question of combining electrolyzers with photovoltaic panels.
Mm-hmm.
So if connected to a 1 megawatt photovoltaic system, how does it work? What is the operating range? Can the multicore be operated continuously if the photovoltaic system power is changing between 200 kilowatt and the full megawatt?
Yes, because we have a nominal operation flexibility of 3 to 105%. That allows that we can follow the photovoltaic peaks. Basically, you need another power supply units. So this is then not an AC version, then we need a DC version. It is possible, it's under development, honestly. It's not finished yet, but this is a plan to have a product where you can do this because we use standardized products, power supply units from the automotive industry, and this allows us also to work with DC. And this is basically what you need for photovoltaic.
Okay, so some adaptations needed.
Yeah.
And perhaps it's important to reflect again that we have two options to regulate. So you have the production rate of the individual stack itself,
Yes.
or the string,
Correct.
60 to 100%, and then you can decide how many strings you operate at a time.
Correct.
Okay, cool. Then a pretty easy question, I would hope. So why are air-cooled systems or air-cooled units used and not the liquid-cooled version? I think that's not correct as asked.
Yeah, but let me explain. I think I understand. So the power supply units are air-cooled. They are in the electrical compartment. The stack modules itself are not cooled directly. So we have the electrolyte, and this is air-cooled. But as I mentioned before, you can also extract the heat and bring it to a heat exchanger and use the waste heat of our product here. Maybe I can show the slide. Yeah. this is the electrolyte is cooled, but it's with a glycol loop cooled, so you can also connect a heat exchanger and use supervised heat. Basically, that's it. This is not air cooled. This is air cooled, correct? Because this is our demo multicore. Yeah, we have the roofs we have the fans on the top of the roof.
Yeah. And the question that refers to that is if the cooling is done through the electrolyte.
Yes. Yeah. Cool the electrolyte down to 55 degrees.
Okay. Going back to the water quality, which was defined as 5 microsiemens per centimeter.
Yes.
The question is if that pre-water treatment should be done on the customer side.
Yes, this is part of the integrator scope. This is not in our container, the water purification system. This is a frequently often asked question, but this is part from our partners. So it's not part of the container.
Yeah. Okay, thanks for that. There's some additional questions on that. So it's asked if the multicore once delivered to customer site is ready to start, or if there's something else that should be installed on a site that doesn't come with a multicore.
Yeah, you need a trafo station, something like this. This is not a part of Enapter, so we deliver the electrolyzer here. And of course, they work with one of our partners together, and they deliver the rest of the necessary auxiliaries there.
Yeah, correct. So
lightning protection, you need lightning protection, of course. All of this is necessary for this product. So you have to do some site works.
Yes. Okay. Thanks for that. Seems we're getting to the last question for now. It's a bit a longer one. So it refers to the power. In the data sheet, it is written 3 to 105% of nominal production rate.
Yes.
How to explain this to the customer? It usually means that the system can be operated at higher power density only for a certain time.
Yes,
for
correct.
how long can it be operated at 105%?
So this is not evaluated yet. We can operate on a higher current. So this is basically possible. It is not, we shouldn't do this all the time. So we are testing this currently in our prototypes. We don't have the correct time yet, how long you can operate here to 105%. But you can operate at 3%. This is not a problem. Yeah, as I mentioned, you can shut off the strings individual, and then you can reduce current there, and then you can operate in this area without any problems.
Okay, perfect. And then perhaps a more general question referring to this one. So why are we following this strategy? For the customer, it means that the system cannot be operated at the maximum power density continuously.
It can operate at 100% all the time, so constant. So should be an issue. So we have the stacks, and the stacks we expect the operating hours so 35,000 hours, and with 100%, this is given by 100% nominal production range. So okay. 210 norm cubic meters per hour.
Yeah, so I hope that answers it. A question on commissioning time. So a lot of questions coming in. So what is the required expected time for the multicore commissioning once everything on the customer side is ready for start?
So this is a really good question. We learned a lot during our prototyping strings. So of course you need a few times. So the good thing is we learned a lot of things, but we expect at least, so let me say 3 weeks, 2 to 3 weeks for the multicore to have the IO checks and to have everything keep running here.
Okay, thanks for that. Another one coming in from Jeremy just now. So what type of material do you use to isolate each work area from a gas leak in the container?
Gas leak into the... Can you repeat the question, please?
What type of material do you use to isolate each work area?
I think the process compartment to the electrical compartment I guess. This is a welded wall in between, and there's no gas coming through. Then we work with an overpressure on the electrical compartment. So we have permanently overpressure here that it's not possible for hydrogen to go to a hole through this wall. We have no holes in this wall, but basically this material is steel here.
Okay, thanks for that. That takes us really to the last question before we move to the next presentation. You mentioned the 500 kW version of the electrolyzer, and it maybe more relates to the BT team, but they are asking when the 500 kilowatt version could be available for customers. If it is the same as a multi-megawatt.
You mean the half megawatt multi-core?
Correct.
So it will be available basically after our 10 products which we want to sell here, because it's very simple to have the design works and to reduce the numbers of stacks. So, but I have no fixed time here for you.
Yeah, and for more details, please reach out to us.
Yeah,
and
reach
we
out.
can give you an estimate.
Oh.
Okay, perfect. Florian, thanks a lot for being available, for answering so many questions, and for your nice presentation.
Thank you.
So next on the stage is Philip. He's already here, and he will guide you through all the news and helpful features of our handbook.